Welcome, students. In this video, I thought I would just take a moment to work through a challenge problem that I've given you in the worksheet, the lecture workbook. This is on page, let's see, currently it's on page 131, though that may change depending on the version of the lecture workbook that you get in the future. But right now it is at the end of chapter 9, and it is practice problem at the end of the chapter 9, practice problem 5. This is what we might call a complex calorimetry problem. It's called complex because it has a few moving parts, a few parts to it. And these complex calorimetry problems can be a little bit challenging from some students. So I thought I'd work through it with you here so you could see how I'm approaching it. So as we look at the problem, it says a student heats a 25.0 gram piece of pure iron to 215 degrees Celsius. So we're going to treat that as the initial temperature of the iron. It starts out, assuming that the student has heated it to that temperature, it starts out at that temperature, 215 degrees Celsius. A separate beaker holding 45.5 grams of water is initially at 22.5 degrees Celsius. So what we've got to think of here is we have two samples. We have a sample of iron metal, pure iron metal, that is hot. It's at 215 degrees Celsius. Then we have a sample of water that's relatively cool, about room temperature, at about 22.5 degrees Celsius. The question then says, the student places, probably with forceps or tongs, places the heated iron into the beaker of cool water. And we are asked to calculate the final temperature of the sample of water once the heat from the iron has been transferred from the iron into the water. So the heat is going to go out of the metal into the water. It's going to heat up the water. And at some point, the metal and the water around it are going to reach an equilibrium temperature, the same final temperature. And we're asked to calculate the final temperature of that sample of water once this equilibration has occurred. Now, in more challenging versions of this problem, you might also be asked to consider the amount of heat that was absorbed by the beaker itself, or even in more advanced chemistry courses, how much heat might have been lost to the environment, right? But for this situation, we're not dealing with this. We're just talking about the water and the iron. So we have a system, the iron, and the surroundings, the water around it. And we're going to evaluate the heat that's transferred from the system, from the metal, to the surroundings, the water. Okay? So there are two real challenges to this problem. The first challenge is to set up the problem, start with setting up the problem so that you know that you're going to run two separate calorimetry equations. There's going to be a calorimetry equation based on the iron and a calorimetry equation based on the water. And that's going to let you calculate the Q of the iron as it's losing heat, and it will let you calculate the Q of the water as it's gaining heat. So that's the first big challenge of this problem. The second big challenge of this problem is recognizing that there is a relationship between those two, the Q of the metal and the Q of the water. Because fundamentally, we need to remember that you cannot create or destroy energy, heat energy. It has to go somewhere. So if the metal is losing heat, then it must be absorbed somewhere, and we're assuming it's being absorbed by the water. So we can write that mathematically, that the Q of the metal is equal in magnitude to the Q of the water. That is, the heat lost by the metal is the heat gained by the water. And the signs of those Q values must be opposite signs, because it's a negative Q for the metal, it's losing heat. It's a positive Q for the water because it's gaining heat. But otherwise, the numbers are the same. They just have different signs. So that's the second big sort of thing that students have to grapple with, is realizing that we're going to be able to use that equation to help us out in our math. The third challenge is really just algebra. And there are so many times when it's easy to make an algebra error. I do it occasionally when I'm rearranging, or I'll drop a negative sign. I'm much better about it nowadays because I know what to watch out for, but it still happens. So we've got to be very careful with our algebra. So now that we have the problem, I'm going to stop sharing my screen, and I'm going to show you my whiteboard here, where I have set up the problem, and hopefully you'll be able to see this. I'm going to read out the numbers as we go through, so you'll be able to see what we're doing here. So I am first writing down the information that we are given in the problem, and that is in blue here. So I have a piece of iron. Let me label this iron. Piece of iron. There's its mass, 25.0 grams. There's its initial temperature that it's going to start out with when it's hot, right? When it's been heated up, 215 degrees Celsius. I have a beaker of water, and the mass of the water is 45.5 grams. And its initial temperature, because it's relatively cool, room temperature, the water is 22.5 degrees Celsius, initial temperature. And this is for the iron initial temperature, which is different from the water. Their initial temperatures are different, right? And then the problem says I'm going to take the iron and put it into the beaker, and then they're going to equilibrate at some temperature. The heat is going to leave the iron and go into the water. So the iron is going to get cooler. The water is going to get warmer. They're going to stabilize at some final temperature. And we are asked to calculate what is that final temperature. And that final temperature is going to be the same for the water and for the metal, right? So all I have done right there is I have written down what the problem has told me. The next stage is to realize I have two separate calorimetry equations that I'm going to set up. I'm going to set up one for the Q of the iron equals the mass of the iron times the specific heat of the iron times the delta T of the iron. And a different calorimetry, another calorimetry equation for the water. Q of the water equals the mass of the water times the specific heat of the water times the delta T of the water. Okay. And here in black, I plug in these values for the Q of the iron, and I get down to right here. You can see how I've simplified some of the numbers. T final minus T initial for the iron for the delta T. I don't know T final, so I can't resolve that, but I know what T initial is. So I put it right there. For the Q of the water, I plug in numbers, and again, I'm going to put in T final minus T initial here. Let me make sure that you can see that. There we go. T final minus T initial. Well, the T final over here and the T final over here are the same, right? Same T final. So that's why I have written it in black to remind me, oh, that is the same T final as this one. Okay. All right. And then we simplify these numbers, multiply these numbers together, and we get that number. And T final minus 22.5 degrees Celsius right over here. Okay. So now I've taken each of these equations about as far as I can, but each of these equations has two variables, Q iron and T final, Q water and T final. Well, you can't solve an equation with two variables, so what do? If you have two equations with two variables, you can set one equation in terms of the other. So basically, you're going to substitute into one equation the values from the other. And that's what we do. So recognizing that the Q of the iron equals the negative value of the Q of the water, that's what I do down here. So I bring down this information for the Q of the iron, and I put it right there. And I bring down this information for the Q of the water, and I put it right there. And then I introduce this negative sign right here. So now I have Q of the iron equals a negative Q of the water. Okay? And now you can see what I've just done. I have resolved it into, I have simplified it into one equation, condensed it into one equation, and now there is only one variable. It's T final. It occurs on both sides of the equation, and furthermore, it's locked up in these terms that I have to deal with algebraically, but the rest is algebra. Okay? So let me tell you how I dealt with the algebra so you can follow what I'm doing here. In order to get T final, and let me make sure that that's easy to see, the T final right here. In order to get that T final alone by itself, I have to get it out of this term in the parentheses. So you may remember from algebra that the way we do that is if we have a coefficient like 11.1 multiplied by something in parentheses, like this, an operation in parentheses, we have to distribute that coefficient. So I multiply 11.1 times T final, and I get 11.1 T final. And then I distribute it again, 11.1 times a negative 215, and I get a negative 2386.5, right? I could certainly round that at this point if I wanted to, but that's the number that I get when I do 11.1 times 215. So on the left-hand side of the equation, I've now got 11.1 TF minus 2386.5, okay? I'm going to do the exact same thing on the right-hand side. I'm going to take this a negative 190.37, and I'm going to distribute it to each of these terms in this in the parentheses. So when I do a negative 190.37 times TF, I get negative 190.37 TF. And then when I just multiply a negative 190.37 times a negative 22.5, I get a positive value. Negative times a negative gives a positive 4283.3. Okay. And now you can see it's the T finals have now been pulled out of those parentheses. So now what do I do? Well, it's just continuing my algebra. I want to get T final alone by itself. So first of all, I'm going to add I'm going to add a 190.37 T finals to both sides. When I add it to this side, this term goes away. When I add it to this side, I get to 201.47 T finals, right? And then I need to add this value, 2386.5, to both sides. When I do that to here, this side, it goes away from my left side. When I add it over here to this 4283.3, it now gives me 6669.8 on the right-hand side. So I've circled this equation here. We're not done yet, but I think you can see that now we have gotten to a very simplified form of an equation where you should be able to have no problem solving for the unknown, T final. So how do we do that? To get T final alone by itself, I divide both sides by 201.47. And when I get that, I get T final equals 33.1. So there you go. That's how we do this. Again, this is a more complex calorimetry problem because you have to do two different calculations, set them equal to each other using our Q of the system equals a negative Q of the surroundings, and then do some really kind of clunky algebra, but eventually get the correct answer, right? So yeah, again, I think in the lecture workbook, it says that the answer is 33.1 degrees Celsius. I'd have to check to see if there's a reason that we need to keep that tenths place. There might be, yeah, there might be a reason to keep it because of down here, when we do this multiplication, we end up having at least 3 sig figs in this answer because this should be 2390, 2390. So you'd have 3 sig figs here. This should be 3 sig figs. So with that in mind, you would end up with 3 sig figs in your answer. Okay? All right. So complex calorimetry requiring you to analyze 2 different substances, their heat changes, set them equal but opposite sign to each other, substitute in one equation, the values for the other, do some algebra, and you can get your answer. This is the type of calorimetry problem that you will encounter definitely when you go on to more advanced chemistry, like in your 152. You will find a problem, even if it's not calorimetry, you'll find problems where you have to solve for Q system and Q surroundings when you do thermodynamics calculations. So this is a good practice for that. Okay. If you have any questions about any of this, please don't hesitate to let me know. And I will stop for there. All right. Thank you all very much for your attention.